All right, so this is the last example we're going to look at of coupled equilibria. So we talked about how we can dissolve sparingly soluble compounds by adding an acid or adding a anion or ammonia that forms a complex ion. So here is an example that's really, really interesting that happens in the ocean. So I'm showing here a picture of a beautiful, healthy coral reef on the left. Look at all those beautiful colors. And on the right is a coral reef that is not healthy, right? This difference is jarring. And we're going to talk about why this happens. Why our coral reef's health has been compromised, right? So coral reefs are built upon skeletons of sparingly soluble calcium carbonate ions, right? So they have calcium carbonate that have a low KSP, right? So this is their dissolution reaction of calcium carbonate. And essentially, what keeps this calcium carbonate is what keeps the coral reefs healthy, right? The fact that it doesn't dissolve well in the ocean waters is what keeps the coral reef healthy. So, because of these rising concentrations of carbon dioxide in our atmosphere, it increases the acidity in the ocean. And here are all of the equilibria reactions that attribute to this. So we have carbon dioxide in the atmosphere that can become aqueous carbon dioxide when it interacts with the ocean, like sea spray molecules, right? Then so when CO2 enters into the ocean, it forms carbonic acid. This increases the acidity in the ocean. So this carbonic acid is a diprotic acid. So it can hydrolyze in water in two ionization steps. So here are the two ionization steps that have acid ionization constants associated with each of the steps. Now, notice that in this second step, we actually form these carbonate ions, these carbonate ions. So what happens is this reaction gets coupled with the calcium carbonate dissolution reaction in the coral reefs. So if we reverse, so we're basically going to reverse this reaction and then combine it with the calcium carbonate dissolution reaction in coral reefs. So I've just simply reversed this and coupled it with the dissolution reaction in the coral reefs. Notice that, so the reason that I'm doing this is to essentially combine these two reactions. But the reason that they couple together is because this CO2 in the atmosphere goes through these coupling equilibriums in the ocean, right? These reactions in the ocean that yields these carbonate ions. So it increases the amount of carbonate ions in the ocean. In the ocean. So if we couple these two reactions together, so since we reverse this one, our new Ka2 is the reverse, and then we have our KSP for the dissolution of calcium carbonate. Here is our overall reaction with its associated K value. Now, notice how high that K value is, right? Compared to the KSP associated with calcium carbonate dissolution. That's really large, right? So what that means is that coupling these two reactions yields a equilibrium constant that's much larger than the equilibrium constant associated with this dissolution reaction. And so we've greatly increased the solubility of calcium carbonate in coral reefs. And remember, this calcium carbonate is what keeps the coral reefs healthy, right? This solid that accumulates on the coral reef. So because of the CO2 in the atmosphere, right, dissolving into our oceans, making them more acidic, essentially breaks down, right, increases the solubility of the calcium carbonate on the coral reefs. And so this is why our coral reefs are, their health is declining due to this increase in CO2. So this is an application that we see in the ocean of coupled equilibria. So I am going to pause here, and this concludes equilibria. So we have exhausted equilibria. We've talked about the fundamentals of equilibria. We've talked about it specifically within acid-base chemistry. And then we've also talked about it with dissolution reactions, right? When we're dissolving a solid. So dissolution, right? The equilibrium between dissolution or precipitation, right? Forming back into a solid or forming a precipitate. And we've also talked about equilibrium in complex ion formation or coordination complexes.